Now we'll talk about a number of individual topics in GI physiology. Let's start with the Brunner glands. Brunner glands are located in the duodenum, which you can see here. They are located in the submucosa, and they are the only glands in the submucosa. Brunner glands secrete an alkaline mucus that helps to neutralize acid from the stomach. Can you guess whether Brunner glands increase or decrease with peptic ulcer disease? Well, let's think through this logically. Since Brunner glands need to combat the increased amount of acid, they hypertrophy in peptic ulcer disease. Therefore, you're going to have more Brunner glands in the case of peptic ulcer disease. Okay, let's next go over pancreatic secretions. To start off with, you'll want to keep in mind that pancreatic secretions are kept isotonic through the actions of the chloride bicarb exchanger on the acinar cells. During periods of low pancreatic secretion, the exchanger's activity is lower and the fluid is richer in chloride. While during periods of high secretion, the exchanger is more active and the fluid is richer in bicarb. As an aside, do you know of a genetic disorder that involves this enzyme and which manifests with respiratory as well as GI symptoms? That's correct. It's cystic fibrosis. Okay, so let's go over some of the direct pancreatic secretions. Alpha amylase is involved in starch digestion and is secreted in an active form. There are three enzymes that are important for fat digestion: lipase, phospholipase A, and colipase. The protein digestion enzymes are secreted as zymogens, which are inactive precursors that must be cleaved to become active. Examples of these are trypsin, chymotrypsin, elastase, and carboxypeptidases. The most relevant one for us is trypsin, which is secreted as trypsinogen and requires enterokinase to be converted to the active form. Enterokinase is secreted from the duodenal mucosa. Once trypsinogen is converted to trypsin, trypsin can then activate the other proenzymes, as well as more trypsinogen, so that it's a positive feedback loop. Now that we've gone through pancreatic secretions, let's go over how carbohydrates are absorbed. How are sugars absorbed by our gut? Well, only monosaccharides can be absorbed by enterocytes in our intestines, so processing all those different enzymes is absolutely necessary. Carbohydrate digestion is accomplished with essentially three different steps. Where does starch digestion begin? Well, starch digestion begins at the mouth with salivary amylase, which hydrolyzes the alpha-1,4 linkages in carbohydrates to alpha-dextrins. Since salivary amylase digests only a small number of polysaccharides, we have the pancreatic amylase that is released into the duodenum that will hydrolyze oligosaccharides to disaccharides. Finally, brush border enzymes convert oligo and disaccharides into monosaccharides, and this is actually the rate-limiting step in the entire process, and this prepares carbohydrates for absorption. Once these have finished their work, monosaccharides can subsequently be absorbed by the villi. This is why people that have deficiencies in the brush border enzymes we talked about before, such as people that are intolerant to lactose, a disaccharide, experience unpleasant digestive abnormalities. The three major monosaccharide units are glucose, galactose, and fructose. Glucose and galactose are taken up by the SGLT1 transporter, which is a co-transporter with sodium. Fructose, on the other hand, is taken up by GLUT5 and is not dependent on sodium. From the enterocyte to the blood, these molecules pass through the GLUT2 transporter. A test known as the D-xylose absorption test is used to distinguish malabsorption caused by mucosal damage from other causes of malabsorption, since D-xylose does not require pancreatic enzyme processing to get absorbed. If a person with pancreatic insufficiency consumed D-xylose, what would you expect to see? Well, you would expect D-xylose to appear in their blood after sufficient time, because again, the pancreas isn't necessary for absorption of D-xylose. However, if they had GI mucosal damage, which meant they were unable to absorb monosaccharides, no such D-xylose would appear in the bloodstream. Okay, now that we've talked about carbohydrates getting digested, let's also talk about vitamin and mineral absorption. There are 3 major sites in the intestine for absorption of 3 key vitamins and minerals. The duodenum absorbs iron, which is in the ferrous or Fe2+ form. Folate is absorbed by both the jejunum and the ileum. The ileum also absorbs B12. B12 absorption is highly tested because of the requirement for intrinsic factor for absorption to occur at the terminal ileum. Bile acid is taken up in the same location. A good mnemonic is iron first, bro, to help you remember the order of vitamin and mineral absorption. Iron, then folate, then B12. Let's do another flash quiz. What are the 3 basic enzyme groups that digest carbohydrates? That's right. It's the salivary amylase, the pancreatic amylase, and the oligosaccharide hydrolases. Next, we'll consider Peyer's patches, which are quite important in host defense. These are unencapsulated regions of lymphoid tissue, and they are found in the lamina propria and submucosa of the ileum. They have specialized M cells that take up antigen. What type of immunoglobulin do they secrete? Well, they secrete IgA. When IgA is first produced, it is secreted into the gut lumen with an attached secretory component, which protects the IgA from potentially dangerous gut environment. Let's next talk about bile. Bile is an extremely critical bodily substance, one that comes up a lot in GI pathology. So let's now go over its physiological functions. Bile is a dark green, yellowish-brown bitter fluid that is produced by the liver. It is composed of various bile salts, as well as phospholipids, cholesterol, bilirubin, water, and ions. A bile salt is basically just a bile acid that has been conjugated to either glycine or taurine to make it water-soluble. Cholesterol 7-alpha hydroxylase is the rate-limiting step in bile synthesis. Bile is the only mechanism the body has to excrete cholesterol. It acts as a surfactant to help emulsify fats in food, which is necessary for digestion of triglycerides and micelle formation. Interestingly, it also acts as an antimicrobial. Bilirubin, as we just said, is one of the many components of bile, but its production is a bit complicated and also well studied, so we'll consider it in detail here. What is bilirubin? Well, bilirubin is actually a product of heme metabolism. Heme is removed from the blood by hepatocytes, conjugated with glucuronate, then excreted in bile. If bilirubin accumulates, which could be due to a problem taking up bilirubin by the hepatocytes, or an inability of the hepatocyte to excrete bilirubin, or even a difficulty excreting bile from the body, the end result is jaundice. You'll hear a lot about direct versus indirect. What does this mean? This simply refers to the way that the hospital's lab tests for the amount of bilirubin. The lab measures the total bilirubin, and it measures the conjugated bilirubin, which it calls direct. Thus, the value for the so-called indirect bilirubin is calculated by subtracting the direct from the total, hence the name indirect. So remember that direct is water-soluble because it is conjugated by the liver, while indirect is insoluble. Let's go over the process of bilirubin excretion. Here in this diagram, you can follow along each step of the path as bilirubin is produced and then excreted. As you recall, RBCs contain heme, which is broken down to unconjugated bilirubin by macrophages. and the bilirubin by itself is insoluble, but when it's bound to albumin, it becomes soluble. The hepatocytes take up the bilirubin, conjugate it using glucuronyltransferase, and then excrete it into the bile. In this diagram, we can see what happens to the conjugated bilirubin once it's excreted in bile. The bile is excreted into the duodenum, and bacteria in the gut act on conjugated bilirubin to form urobilinogen. Most of this, about 80%, is excreted in feces as stercobilin, which is responsible for the color of stool. However, 20% of the urobilinogen is taken back up at the ileum. Of this, 90% is returned to the liver along with other components of bile. However, 10% passes to the kidney and is excreted as urobilin, which gives urine its characteristic color. Let's now do a board's relevant question to integrate what we just learned and also provide an intro into our next section, pathology. Let's now do a board's relevant question to integrate what we just learned and also provide an intro into our next section, pathology. A healthy 25-year-old man comes to the physician for a routine examination. His laboratory tests show a serum bilirubin level of 4 milligrams per deciliter and a direct bilirubin level of 0.3 milligrams per deciliter. The patient's liver function tests are normal. Which of the following best explains the patient's serum and indirect bilirubin levels? Is it A, defective bilirubin excretion, B, extrahepatic biliary obstruction, C, glucuronyltransferase deficiency, D, heme oxygenase deficiency, or E, intrahepatic biliary obstruction? Okay, let's go through this systematically. The patient is a young man who is healthy and comes in for a routine exam. His levels of direct bilirubin or conjugated bilirubin is 0.3, whereas his total bilirubin is much higher at 4. This means the patient has an indirect bilirubinemia. Since he's healthy and young and has normal hepatocytes, this suggests that it is most likely due to a glucuronyltransferase deficiency, which we will go over in more detail in the next section. For answer A, B, and E, this isn't correct since defective excretion or biliary obstruction would increase both indirect and direct bilirubin. D isn't correct since a defect in heme breakdown wouldn't elevate indirect bilirubin specifically. Hence, the answer is C. We have now gotten to the end of the GI physiology section.